be presenting along with my colleagues results and activities throughout the year. So the PRELUDE project it's ending it's near the end of its life. The end of the year, so we take this opportunity to present some major achievements. The PRELUDE project mostly has to do with advanced building monitoring in order to bring correct, in order to achieve proactive optimization and building control. So we tried to integrate innovative and low-cost solutions throughout several pilots and optimize energy use in households. We are a consortium of 21 members, and we operated in 8 pilots. And the key targets of the activities were, first of all, data predictive control in order to enable proactive building optimization, predictive maintenance to be applied in residential buildings, smart renovation schemes, a free-running model to optimize building with passive cooling and ventilation, and neighborhood focus by optimizing buildings within same districts, and the use of multi-role fiber optic sensors that allowed more exact and versatile measurements. So, starting things off, I will start with what my company did for the project, which was to provide the software solution to bring all of these things together. So now looking to the project from a software point of view, basically what do we have? We have a building where we have a series of sensors. We get data from this building. We provide those data to different technology providers. Some calculations are made, and the building is improved. This is the high-level, let's say, goal and how we idealize the idea of the software infrastructure in such a case. Now, what is the reality? The reality is that different technology providers work with different buildings in different ways. The technology providers need to collaborate among themselves. The target user is not just a tenant, but there are different types of users that have different needs, so we also need to accommodate about that. Some technologies do not rely only on real-time data from the buildings, but also need historic sources in order to perform, for example, model trainings for artificial intelligence in order to achieve higher level results. So all of this creates a certain complexity that needs to be somehow controlled. And another point here that is also important to mention is that throughout our project, we didn't try to enforce solution to different buildings. So a pilot building in one case may use X sensors, a different building may use Y sensors. These have different protocols, different rates of communication, and so on. So we have to accommodate for all of those. So what we bring forward is a middleware solution, which we call Physics, and we will see about it in a little bit. And the idea is that this is a software solution that basically sits in the middle of the whole thing, and everything communicates through the middleware itself. So a technology provider, someone who develops, let's say, an artificial intelligence model or a prediction model and so on, doesn't really have to care how the building provides data. He or she doesn't have to care about the rate of transmission, the security, how to get the data, how to store it, and so on. All of this is handled by the middleware, and all the technology provider has to do is say, okay, I need temperature data for the last 3 months aggregated by hour, and that's it. How the middleware gets that, it's the middleware's problem. So that's the general idea of what the middleware does. Since we have all of this functionality in the middleware, it makes sense then to not only handle the communication aspect, but also handle the storage aspect and some common facilities that are needed throughout the application. For example, some sort of pre-processing of data, data filtering, and so on. All of this can be handled through the middleware. And this is where our solution comes in. And this is the physics framework. So what that is a generic framework to allow the development of decision support applications and is meant to be agnostic to the domain. So smart buildings in this case could be one, smart grids can be another, other domains can also work. So what we try to do is basically abstract all of the data sources that we have, regardless of what they are, monitor data, model results, calculations, aggregation, and so on, and create a single cohesive model that fully describes the application that we want to do. So in this case, we have the PRELUDE project. So in this case, we have the PRELUDE data model. So all of the partners, in this case, stakeholders in the future, know that when they need data from a building, from an external weather provider, from a model, from whatever, they know how to get it. There is a cohesive single way to get that, and the data has a specific structure and hierarchy that allows this sort of communication. So the general idea is to take away the complexity of writing software, in the sense of software, and allow engineers to focus on their domain of knowledge. Because we do not really want people that have, for example, PhDs in computer science and building renovation and building management to have to handle low-level APIs, data storage, and all of these things. We handle that, and we allow scientists and engineers to do their thing without all of these limitations. So the physics at a very high level, and I will go a little bit quickly here, is it has 4 distinct elements. The information model is what I already described. It's basically the way we virtualize information for an application. Agents are just simple functions or singular programs that use this information model. Either they get data from it or provide data to it in order for others to use. And all of that, of course, is done through the information model, so other agents can always use what is available. Now, instances of these agents are grouped and deployed in nodes. So I can use multiple server, clouds, edge devices, whatever I have available to scale the application and make something that makes sense, is energy efficiency and data efficient. And there are a series of services that are provided by default through the physics application, the physics framework. And services are basically just agents that are used again and again and again. So if I have a time series aggregation function, I really don't need to rewrite that every time. It's just a single approach that you do that. I will skip that completely. So here is the middleware as it stands in the context of PRELUDE. We can see that it sits in the middle and tries to integrate all of the pilot buildings along with all of the technology providers that we have throughout the project. And of course, the interesting thing here is that no one talks with one another without first going through the middleware. So this is the overarching goal. So everyone knows just how physics works without knowing how everyone else expects to get data, provide data, and so on. As I already mentioned, apart from the data collection, we also have data pre-processing, aggregation, and storage in order to ease all other stakeholders and partners of the project do not have to deal with that. And this is pretty much how it works in PRELUDE itself. So what happens here is, as we described, we have a series of bridges that bring data in the portal, the framework. We do some data management as needed, we store, and then we recycle all of the data throughout the technology providers in order to get the final outcome of the activity. And with that in mind, since we already have pretty much all of the necessary input, we also use the physics framework as the baseline to create a simple user interface and user experience to assist all of the relevant stakeholders. So in that regard, we elected to go with something simple. And what we have is a simple dashboard that has real-time data analytics and historical analysis, a series of events and action logs, and this shows either, for example, threshold violations or situations where an action is triggered or recommended from the PRELUDE portal to be performed. So if, for example, a technology provider says that you need to close the window, close the blind, do an action in your building, this is distributed through the PRELUDE portal. And we use the same simple approach, but with different targets, and we have two different users, one being the tenant and one being the expert. The expert, of course, has a lot of more information and has more detailed graphs and charts and more ways to interact with the data, download it and so on. While for the simple user, the tenant, we try to keep things as simple as possible in order to give the very high-level view of what is needed. Just a few initial mock-ups of what we're talking about here. You can see that we try to keep it super simple. This is a tenant view, by the way. Yes, the goal of the dashboard is just to show very quickly what's going on in your apartment, floor, or building, depending on the architecture. Then we have the events, so we have a list of everything that has happened in the time range that you select. And finally, we have a historic data view. Again, this is only for the tenant, so it's super simplified, where you can see any time range that you want along multiple sensors with thresholds and understand when or how something goes wrong. This is very quickly from my side. Thank you for your attention. And now we move to Pierre from Aalborg to continue.
Thank you very much. I think first I have to say that I'm a stand-in for my colleagues today. Daniel Lehrer is defending his PhD today, so his supervisors are attending this. But I followed the project on the side and I try to do my best. This presentation is about, you could say, one of the technologies that are, or methodologies that are part of the PRELUDE project. And the idea here was to provide a service for district heating connected buildings. And the focus is, of course, for these buildings to improve their energy efficiency, to develop a kind of data-driven building assessment, and also be able to include buildings which have, you could say, different levels of smartness. When we look at district heating connected buildings, we are in a phase where we get more and more information available. More and more buildings have smart meters installed. Some of them are maybe not that smart, but still they do collect a lot of information that can be made available and can be used in time. But it for sure, as time goes by, these meters become more and more smart, collect more and more data more accurately, and probably also, you could say, all of them are capable of communicating these data online, or at least with a very high frequency. So we are moving in a direction where data availability will be increasing. Of course, if we look at the application of smart heat meter data today, the main purpose is billing. And this is also what we can see when we look into what requirements district heating companies have put on these smart meters, that their main purpose was billing. They were not always thinking about what other opportunities could be. But of course, what we want to include in this development is to be able to provide tenants or building owners with more awareness about how their system is working. Maybe encourage behavioral change if it's beneficial for energy efficiency and their bill. We also want to look into, and this is what I will focus a lot on today, is on fault detection. We have collaboration with several of the district heating companies in Denmark, and their expectations or what they think is that up to 50% of their customers actually have some faults in their system. Some quite big faults, some smaller faults, but it's actually quite distributed. And then if we have more information on the actual data going on in the building, we can also use this to make decisions. But of course, there are some things that needs to, or some challenges, you could say, that needs to be overcome to be able to do that. And now, was presented before about storage of data, pre-processing of data, and so on, is of course a prerequisite. But in order to make it useful, there are also some other challenges. For example, if you have a smart heat meter, it measures both heat and domestic hot water. If you want to do some actions based on this analysis, you need to know how much is space heating, how much is domestic hot water. It's different parameters and that controls the amount of energy use. So we need to be able to distinguish it. And then, of course, we also need to ensure that we have some reliable data. For the PRELUDE project, we have based this on different data cases. First of all, we have access to smart heat meters from around 20,000 households from our local district heating company. And there we have hourly data available for almost 2 full years, or for 2 full years of operation. The challenge with this data is that, of course, it's hourly data, but it's also rounded down to integer kilowatt hours. So this means that if you in an hour have used 2.5 kilowatt hours, what is reported on the meter is the number 2. And the 0.5 kilowatt hours is actually moved to the next period. So this means if you just take the readings of the meter, it's actually not only looking at what is used in the period you have for the last period, but it's some of it might be pushed to the next period, and some of it might actually has been gained from the previous period. So it's not that accurate. Then we have, in order to, you could say, validate our methodology, we have provided much more detailed data from 28 apartments. So here we have actually the split between space heating and domestic hot water. And here we do have more precise data where we actually have decimal data on the kilowatt hours used in different periods. And then we also have fault reports from inspection of substations. So this means when a fault is reported, there is a man going out identifying what is the fault. He writes a report, what is the fault he identified and what did he make of changes. So this means we actually have a possibility to see how did the system work before, what was actually identified as a fault, and how does the system work afterwards in these 500 buildings. And we can use this in order to try to identify, you could say, or to develop an algorithm so we actually can identify these type of faults in other households which might not have had a visit from a person. This illustrates, you could say, the two challenges I mentioned. Of course, this challenge with truncation errors or truncation of the data is most important, is quite important in buildings where the energy use is quite low. So this means our highly efficient buildings where energy use might be quite low, because if you only have an energy use of 1 or 2 kilowatt hours per hour, then of course truncation might have a big influence on the accuracy, while if it was 10 kilowatt hours per hour, then of course the difference would be smaller. And then of course the question about what is heating consumption and what is domestic hot water consumption, which is the other challenge. So what we have been doing is actually, first of all, try to develop a methodology to compensate for this truncation, so we, in a way, can predict or what was the actual consumption in the hour we did monitor. So we have used what we call a smooth pointwise move scale algorithm, actually to be able to predict the actual consumption based on the truncated area value. And then afterwards we have developed a methodology to separate space heating and domestic hot water energy use from these smart meter readings. This just shows you could say some of the results. If you look at the upper figures, you can see what has been the fault compared to the real data on the left side, and in green, and these truncated data in red. You could see that there are larger discrepancies or faults, you could say, in the analysis if you use the truncated data. And then the blue one shows this methodology we have developed to actually get more accurate data out of the data series. That works quite well, although of course not as perfect as if we had the accurate data. Then the other thing we have been working on is actually how to present the data, because if you want to make a decision based on some data analysis, you need to in a way have it visualized so you can identify easily what is the challenges. So there we have worked with different tools. On the upper right corner, some data mapping actually to identify where in the system do we have maybe high return temperatures or which buildings are problematic. In the lower left corner, we have a picture on the volume temperature ratio, because what happens when systems fails is typically that the return temperature increases, meaning that we have a lower temperature difference, and then the volume flow increases. So this is a typical signal that something is wrong. And of course you can do that in different ways. We have on the left side, we have a volume temperature ratio. On the other side, we have a relation between temperature difference and outdoor temperature, where you also would expect that the temperature difference would be quite high when we have a low heating need, and maybe higher or smaller when we have a high heating need. So these are some of the methodologies we have tried to use in order to, you could say, illustrate faults in the system. Yes, and then we have developed a fault detection and diagnosis methodology for you could say district heating substations. And there we have the parameters we have used is return temperature, volume flow in the substation, and energy use. And then you could say based on these fault reports, we have tried to identify, you could say, what are the problems. When we look generally of these, you could say, many cases, we have identified different default patterns, which we called the one in the top left corner, we call degradation. So this means here in time over several months, it seems that the system perform worse and worse, having higher and higher return temperature in time. We have one where we call stroke, also where suddenly the return temperature increases a lot. We have the other one, we call it level shift, where we maybe have one level in a certain period, then we have the stroke, and then we have another level later on, and then you could call it level shift with degradation. So there are different fault patterns that we can identify when we look into the data. This picture shows something about what is then the consequences, and here we have looked at different types of technologies, radiators, underfloor heating, towel heaters, and so on. And there we show, you could say, the turn temperature, volume, and energy flow. And it seems when we do the analysis of the faults that the faults we have in the radiator systems actually have an impact on the energy use, which is picture A on the top left corner, while the other faults actually do not reflect very much in the energy use. So these are more, you could say, maybe short-term faults which do not influence if you look at the overall energy use. But they do increase the return temperature and they do increase the volume flow. So this means it can be critical for the capacity of the system if you have, you could say, increased the volume flow very much. Yes, in the conclusions, we have identified or developed method to pre-process the data series, so we actually get more accurate data as basis for our analysis. We have developed a method to split total heat to the two parts, space heating and domestic hot water. We have also identified some, you could say, indicators and graphical methods in order to facilitate the analysis of the time series. Standardized methods to collect faults. Actually, when we got the first fault reports, every company had their own way to make these reports. So actually, we developed a common methodology for the district heating company that all the contractors they had used the same fault report, so we are sure to get the same information and in a consistent way, because if you don't do that, it's very difficult to apply for developing methodologies. And then we have made some kind of classification of the typical fault patterns and also assigned, you could say, these different fault patterns to a typical fault location. So what is the problem? Is it the district? Is it the heating? Is it the radiator heating? Is it the towel heater? Is it the hot water production? Where do we have the problem? Yes, thank you.
Okay, good afternoon, everyone. I'm Valia Liopoulou. I'm the Energy and Resource Unit Leader at the Core Innovation Center. So basically for us, PRELUDE was the foundation where we started gaining our experience in the building sector, so I'm going to talk about that. So first of all, a little bit about energy efficiency in buildings. What do we basically mean? There are two basic things that we have to target. So it's reducing energy consumption, which can be achieved basically by two things. Technical solutions is the one that first comes to mind for everyone, and the second one is behavioral change. which is really important not to forget. And the second one is optimizing energy use. So basically, how can we optimize which vector we can use for heating? Is it going to be electricity or is it going to be natural gas? And at what temperature should that be? And important is to notice that this we're doing while maintaining or improving overall performance of the building. So a little bit about the landscape in Europe at the moment. So buildings are responsible for more than 40% of energy consumption and more than 35% of greenhouse gas emissions. The targets that the European Commission has set are quite ambitious. We have to reduce energy use in residential buildings by 16% until 2030 and by 22% until 2035. And has adopted basically a very important strategy, the Renovation Wave strategy in 2020, where basically 55% of the energy savings in the residential sector will be delivered through renovations of buildings with very low energy performance. And that actually means that 60% of the worst performing non-residential buildings in Europe by 2030 and 26% of them by 2033 have to have significant improvements in energy performance. And to add something additional, all new residential and non-residential buildings in Europe must have zero on-site emissions from fossil fuels, so publicly owned buildings starting from 2028 and all other by 2030. So we understand that this is quite a challenge. It's not one-dimensional. It's a very complex, multi-dimensional question where we have energy efficiency mixing with the decarbonization. We have demand response programs. We have electricity heating networks. And we have one inherent challenge of buildings, which is the property ownership. So basically, we have multiple stakeholders, from tenants to building owners to building managers to architects and construction firms. So how can we navigate such a landscape? There are many approaches, of course, and I will talk about the Industry 4.0 approach because that's what our expertise is. So basically, how can we approach the building issues that I mentioned from this perspective? So first step is basically to assess the needs in terms of energy efficiency targets and to identify which are the worst performing assets that we have to target, basically, which buildings are the worst performance, have the worst performance. Collecting data, of course, it's a really important step to achieve this. So we need, of course, data. We need the digital infrastructure. We need the meters and other kind of sensors, whatever is necessary to collect this data. But data alone doesn't mean anything unless it accompanies by insights. So basically, if there are no actionable or valuable insights, there's nothing to do with data. So identifying trends, patterns, anomalies in this data, it's hugely, hugely important. And interpreting those is what makes anything of data really valuable. Then it's developing AI models for forecasting future energy consumption and generation. This is something that Core did for PRELUDE. So we developed 24-hour forecasting models for weather and energy. And these are quite important as well, not only because of the predictions they give us, but also because we can plan things. We can plan installations, renewable energy deployments, we can plan demand response programs, we can size better installations and so on. And the next step is the real-time energy management, which is actually optimization algorithms given to reduce peak energy consumption, to do peak shifting, to decide whether we are going to sell energy to the grid or we're going to use it for self-consumption, whether we should shift from high grid tariffs to lower ones, and so on and so on. And finally, this is a tool that we developed in PRELUDE during PRELUDE project, and it's a planning tool basically, and it provides suggestions for future investments. So anybody, building manager, the building owner who wants to invest in any kind of technology, be it a natural gas boiler or a heat pump or a biomass boiler or a PV installation or an energy storage installation, they can use the tool, and this can give optimized configurations according to CapEx, OpEx, according to the grid electricity price, and so on and so on. So a little bit about the applied Industry 4.0. So yes, PRELUDE is the project that we, as I said, basically developed, fine-tuned actually our forecasting, our weather and energy forecasting models, and the project where we developed this offline tool I just discussed. It's almost over, and we're very happy that we participated in PRELUDE. Other projects that we have been working on buildings, well, everything started for us with EDICE. It's a complete project that has been completed, where it was the first project where we started developing our forecasting models. SATO project is another project that's ongoing, and it's also exhibited here in sustainable places in a couple of workshops today and tomorrow. It's about energy-consuming self-assessment and optimization, and basically giving the opportunity to any kind of new and legacy energy devices to have IoT capabilities and to do self-assessment. In PERSO, it's another also project that is also featured in sustainable places, where we basically core is developing the energy management system, so the real-time management system that I showed earlier. And it's about deep renovation and addressing challenges of renovation in terms of digitalization, fragmentation of users, of uses, quality, efficiency, and rapidity throughout the entire project lifecycle. And a new project that is going to be starting in 2015 in Blanc. So this is the goal of the project is basically to create an open ecosystem structured on the economy of data throughout the entire building life cycle, and it aims to include indicators and models on 5 categories: so energy, human, environment, economy, and resilience. And basically what CORE will be doing here will be to, let's say, match the offline planning tool that I showed with the real-time planning energy management system, and develop all these indicators, all the 5 categories. And about us a little bit quick. So CORE Innovation Center is the non-profit organization subsidiary of CORE Group, which is its aim is to basically foster an industrial innovative ecosystem. We have 4 units, the digital transformation, the digital tools, digital twins, and the energy and resource efficiency. We have more than 50 Horizon, basically, Horizon Europe funded projects, completed and ongoing, with more than 20 million of EU funding, 68 members, and more than 300 partners. And yeah, I'm leading the energy and resource efficiency unit. So we're a group of data scientists, project managers, and technical project managers. And yeah, what we're good at is basically, yeah, we're a great team. We work very nicely together. We have access to data from various industries, from the entire built environment spectrum, so manufacturing, processing, and buildings, and basically the solutions we develop are transferable to an industry in another. So yeah, we're developing basically domain expertise in several sectors. And that's all from my side. Thank you very much.
my side. My name is Florian. I'm from University of Applied Sciences Burgenland in Austria, and our part in the PRELUDE project was to investigate predictive controllers for these energy management systems, which we're talking about today. So my colleague Peter and me are both in the team, and we will both have presentations about two demonstration buildings, which were in the PRELUDE project. So first of all, to give you an overview, we will have a short introduction, then we have a look at the building model we were using, the predictive control scheme, something about the integration in the building, and in the end we will look at 1 month test period and the results of it, what we achieved within the project. So goal was to define some demand side flexibility on the thermal side, basically, and this is one of the key issues for our transition in the energy sector. And the basic technology is the heat pump, so we are able to transform the thermal loads from the right-hand side basically to the electric loads. And with the presence of these electric loads in the buildings, with heat pump operation, we then now can think about how to fit these loads into the existing generation. And we can take a look and think about the local generation of the buildings itself. So we have the photovoltaic systems integrated in the buildings. That's quite obvious. That's the most obvious and best solution because there are no local CO2 emissions at the buildings anymore. Or we have to think about regional generations, which will be basically the electricity markets at the national status or the local status. As I said, for the photovoltaic, it's quite clear that it's a good solution. But also for the electricity market, it's quite interesting solution to use this to use the shift probabilities because in general, you see here the results from 2003. Electricity prices in the markets in Austria, Germany, and Denmark, and overall, we have a good correlation between the share of renewables on the left axis compared to the price we pay for it. Yeah? And independent how this electricity market is set. So, for example, in Austria, we have a high focus on hydro energy. In Germany, we have a quite sophisticated solar peak. And Denmark, the market is driven by wind energy. And nevertheless, which technology is present, we can see this correlation. So if you combine photovoltaic energy, local at the building, with prices, with hourly electricity prices, which are now very common in the European networks, we can achieve very low operational CO2 emissions of our heat pumps and our systems. And within PRELUDE, we were active in 2 demonstration buildings. The one was located at our campus in Pinkerfeld, which is a very complex building with a complex structure, where this predictive control algorithm also need to be very precise and complex. This is the part my colleague Peter will tell about. But on the other hand, we have lots of buildings with a very low technical level. And for example, we were using the building in Denmark, in Egersund, within the PRELUDE project to test the simplified structures of this predictive control algorithms. And what you can see here are the building models. And just to give you an expression, so the building models for this adaptation need to be redefined and make as simple as possible, yeah, in this case. On the other hand, of course, you lose your accuracy of the model, and your control scheme need to address this low accuracy of your model as well. So for to work with such simple models, we proposed some kind of predictive feed-forward control scheme, which you see here. And all you need for the work of this scheme is some kind of weather prediction, which is not a big thing anymore. So you can, the weather predictions are widely available in the web, and most of them are freely available. You need some kind of local generation prediction. It's the same. So as for the weather prediction, if you have a solar prediction available at your building, it's very easy to generate some load prediction of the photovoltaic system. And the third part is the regional generation of the electricity. So you need some kind of prediction of the hourly electricity prices. And again, all this data is available by web APIs in general, so you can easily fetch this into your system. Yeah, so it's scalable, this solution. Then you have to think about combining, on the one hand side, this local generation, which is the photovoltaic system in general, with the regional generation. And this can be easily done for the heat pump with some kind of thermal price profile. So this is the first part you need to do. At first you have cents per kilowatt hour electric energy, and by calculating very easy calculations, you can transform it into cents and euro cents per kilowatt hour thermal energy. In this way, you can integrate as well as the local generation, as well as the efficiency of the heat pump, which might be different at different times of the day as well. That's one of the key aspects. You have to do it first. And from the building model, you're just generating the demand of the heat of the building for the future. So we are talking about predictive schemes, which means that we are controlling more or less the future. And therefore, we need to know how much energy, the thermal energy in this case the building will need, for example, the next 3 days. This information is gained from the building model. And in the end, you put this information together, and all you do is searching for the best times to provide the needed energy, the required energy from the building with the cheapest thermal price. And this is done by some kind of numerical optimization. And you see on the top, the thermal constraints of the building are again considered in this optimization. And what you get on the right-hand side is some kind of operation plan, which tells you how to operate the building in the future. And this operation plan is then sent to the building, and the heat pump can operate along these plans. And what's very common or forward control scheme is that the information is transferred from the left side to the right side, and only in this direction. So we have a feed-forward scheme without a loop. So we do not feed any information from the building back into the system. And therefore, it's also, so it's quite simple, yeah? And it may not be the accurate one, but still it's very scalable, and you can use the same algorithms and same parameters for lots of different buildings. So that's the big advantage of it. On the other hand, if you have now these results of the operation plan and of the numerical optimization, you need to interact with the specific building as well. And therefore, on the left-hand side, you have now the results, and this could be cloud-based, for example, for higher scalability. On the right-hand side, we add now our building. And what's new in this approach is that we are trying to still use the existing local controllers, which are acting there. So in this case, we have the heat pump in gray, and then we have 2 boilers. The one is for domestic hot water, and the other one is for the underfloor heating system. And in addition, there's some room temperature local set point controller also active. And we are just translating the set points from the numerical optimization, which is more or less on-off values for the different systems, to adapted set point schedules for the 2-point controllers which are active in the system. So on the one hand side, we have the advantage of an optimized strategy, but on the other hand, we have the robustness of the local controller, and we still can gain the thermal comfort inside the building. Just to give you an impression, of this work and of the test period in February 2024. You see on the top graph the temperatures. In blue the indoor temperature and in black the outdoor temperature. It's just 1 week or 8 days. And you see basically the temperature inside the building is quite stable, although we were shifting lots of thermal energy from one time phase to another. And in the second graph, you just see the set points of the 2-point controllers, which were activated by the optimization results. And here are the results itself. So in the first figure, you see in red the photovoltaic energy provided by the local system, and in black the electricity consumption from the heat pump. And in the lower figure, you can see the prices, the electric prices of the grid there. And if the heat pump is using energy from the grid, it's marked with some dots. Yeah? And the black dots are used electricity without photovoltaic energy, and the red dots is where the system combines photovoltaic energy and the electricity from the grid. And there are some quite typical peaks inside. So this is always a few hours in the winter months where the local grid operator adds additional costs to the electricity to prices and to lower the load at these critical time periods. And this is also integrated, of course, in the system. And what you basically see is that these peaks are more or less not used, so they are avoided by the system, except the very first one, which the domestic hot water failed. In this case, because there was some use of domestic hot water, and so the peaks are avoided, and the valleys are more or less consumed by the grid. Also quite interesting, if you take a look at the February 22, so you have here during the day a little bit of photovoltaic energy, but the controller sees in the future, okay, there will be on February 23 in the night very, very cheap electricity from the grid, and in this case I'm still avoiding the electricity from the photovoltaic system and are waiting for this cheap electricity from the grid. And in the night between 22 and 23, he is consuming through several hours electricity from the grid because it's just was cheaper than the electricity from the photovoltaic system in this case. Okay, and 24, for example, you see the small values, so it's quite accurate. All in all, if you sum up this month, we achieved about from the photovoltaic energy, about 70% was consumed directly by the heat pump without a battery system, which is installed there. Just the direct consumption is 70%. And of course, you can also lower the electricity price for the customer, on the other hand. In this case, in this 1 month, of about 15%. Okay, that's from my side, and Peter, who has the complex building at our campus. So this was the simple one.
Good afternoon. I'm Peter Klanatsky, and as my colleague Florian told you, I give you in the next 12 minutes a short overview about our investigations of the long-term performance of a data-driven model predictive control system in a real office building. Because of the time, I have to give you only, or I can give you only a short overview about the main topics, and these are the main features of the real office building and also the hydraulic concept for heat and cold supply. I will give you a short overview about the developed data-driven model predictive approach, and then I will give you a summary about the results of the long-term test. The main features of the real office building are we have an office building with nearly the whole south and west facade is a triple glazing facade with external and internal shading devices. The building was built in 2014, has approximately 600 square meters usable area, and has also technical building equipment as shown. For example, we have an air conditioning system to ensure the hygienic air exchange rates. We have a gas boiler for space heating. We have a heat pump for space heating and space cooling. We have a hot and cold water storage tank. On the other side, we have on the building's roof a PV system, more or less 20 kilowatt peak. And as I told you, we have a triple glazing facade with internal and external shading devices on both floors. And to sum up, we have also 3 static heating or cooling surfaces. One is in the floor, one is in the near surface of the ceiling, and one is a concrete core activation. To control the whole building, we have to consider all thermal zones in the building. So in the ground floor, we have 3 thermal zones, and in the upper floor or in the first floor, we have 6 thermal zones. Each of the thermal zones, we have to consider the underfloor heating system for space heating. We have to consider the near surface cooling system in the summer months, and also the storage tank. And what we don't have to forget is the triple glazing facade in combination with the external shading devices. So each of them we have to consider in our solution approach. The hydraulic concept of the building is shown on this slide. I know it's very small, but I give you a short overview of them. We have a gas boiler with the number 2. We have the reversible heat pump with the number 1, which can operate for space heating and space cooling. We have a heat exchanger to use the waste heat of the heat pump to feed into the hot water storage tank. We have the heat pump can operate on an air source, so we have a recooler on the roof of the building, or we can also operate the heat pump with some different ground heat exchanger. You also see the storage tanks and the distributors of the hot water and cold water. And to sum up, if we talk about the long-term test of the DMPC approach, we have to consider the standard or the baseline or the operating mode of the baseline. So the didn't work, so I give you this figure. And the baseline was that we operate the building with the gas boiler for space heating, more or less the heat pump for space cooling, and we used the recooler for the heat pump. Yeah? So the air as source. And for the long-term test, we made, before we start the long-term test, we made additional measures to save energy. So we deactivate or switched off the gas boiler. We used the heat pump for space heating and space cooling. We used also some of the ground heat exchanger, so we don't use the recooler on the roof of the building. And we more or less, we also switched off the reheater of the air conditioning system to avoid non-critical energy consumption in the summer month. So these are additional measures we have to consider if we look at the results of our long-term test. How will our DMPC approach work? So that our approach can work, we need information from the experiment. So we need from the building and from the technical building equipment current values and also historical values. With the historical values, we can parameterize the gray box models which we used. One model for the storage tank, and for each thermal zone, we use a gray box model. Yeah? So we have 9 thermal zones. We used, therefore, 9 gray box models, and all of the parameter of these gray box models we have to parameterize. So we use the historical data, more or less the last 42 days, to parameterize this gray box model. And with this gray box model, we need further information. We have models to we can talk about digital twin here, to describe the thermal behavior of the thermal zones and also of our storage tank. The storage tank is in the summer month the cold water storage tank, and in the winter month the hot water storage tank. So we only can operate in one way for numeric optimization, more or less the winter or the summer operation mode. We also need a weather forecast. We need a model of our PV system to make a forecast about the yield of the PV system. We can make with the historical data a forecast about the internal loads, and we also need the energy demand of our air handling unit. So how much energy the preheater or the cooling unit needed for the next forecast horizon, for example, the next day or 24 hours. In combination with all this information and the objective function and the constraints, which are the thermal comfort in the thermal zones or the temperature which we need in the storage tank, we can, our solver, our numerical optimization, Gurobi, we use Gurobi for that, can calculate the optimal control inputs in that way that we minimize the predefined cost function. If we got the control inputs, we can use the control inputs for the actors of the experiment. So we can switch on or off in summer the heat pump and the storage tank. We can switch on or off also the near surface cooling system in each thermal zone individual. And we also consider the external blinds of the shading elements of the triple glazing facade. So if we talk about the cost function and we minimize the costs for the electricity for heating and cooling, the lowest or the operating mode without cost is that we don't use the heat pump in summer months and we only activate the shading elements, that we have 100% shadings and we can reduce the solar loads. These all effects consider our numerical optimization process, because the cost for the shading elements is zero, and if we need electrical energy, our numerical optimization process consider if we have a yield from the PV system for the next hour, or if we have to buy from the grid operator electricity. And in the winter mode, we have the same in that way that the reversible heat pump is switched to the winter mode, and that we use the hot water storage tank and the underfloor heating system. And in the winter mode, we also can use the external shading elements to heat up our rooms. So we can use the external shading elements to warm up our thermal zones, and therefore that we need less electrical energy for heating up the hot water storage tank, and therefore for switched on or off of the underfloor heating system. As I told you, we also have internal shading elements, so to avoid glazing and so on, the colleagues in this room can use the internal shading elements. I will come to the results of our DMPC approach. The first slide shows you the cumulative energy demand for heating. The continuous blue line is the energy demand for heating of the reference year. The reference year is the year from June 2018 to June 2019. The red continuous line is the energy demand of for heating during our long-term test with the DMPC in combination with all other measures which we have taken. And the dashed blue line is the calculated adjusted baseline according to the International Performance Measurement and Verification Protocol. And as you can see, if we compare the calculated adjusted baseline with our measured cumulative energy for heating, we have a reduction of 34%, more or less 14,000 kilowatt hours of energy demand. If we made the comparison in the same way for the some mistake by combining all PowerPoint presentations. Sorry for that. We don't have the figure for the cooling energy demand and for the final energy for heating or cooling, but the table on this slide shows you the values. So as I told you, we have a reduction of more or less 14,000 kilowatt hours for the energy demand for heating. We have a reduction of more about 19,000 kilowatt hours for the cooling energy, which is compared to the adjusted baseline more or less 79%. And if we compare the final energy for heating and cooling, so the sum of the gas and the electricity, we have a reduction of more or less 58,000, which is more or less 85% reduction. Please consider that the adjusted baseline is a calculated baseline, which is the energy demand for the period of the long-term test, if we had not implemented any measures. Yeah? And if you remember, I told you that we made the decision that for the long-term test, we also switched off the gas boiler and use only the heat pump for space heating and space cooling. So therefore, the 58,000 kilowatt hours is a huge amount of them. Also, the reduction of gas, so we don't have a gas consumption during the long-term test period. Yeah, that's in short overview about our investigations. If you detailed information, you prefer or you can refer to this publication listed below, and some of them are available and some of them will soon available. Thank you for listening.
Hello, everyone. Thank you for attending this workshop and especially this talk. I'll be talking about smart district heating, scalable and trustworthy forecasting with advanced AI. My name is Kais Dai. I'm a senior data scientist at Trilogic. Trilogic is a R&D performing company providing solutions in using big data and artificial intelligence technologies, and we are participating in several European projects, H2020 and Horizon Europe projects. PRELUDE is one of them. These are some other projects. And our commercial brand, which is Trilogic, is we are providing all these organizations to help them to build their information systems with big data and artificial intelligence technology. Well, this work comes as part of the PRELUDE framework. As said before, we are 21 partners working in around Europe, and we have 8 pilot sites. Well, to put you in a context, effective energy demand forecast is essential for energy production, for optimizing energy production, and this is by enhancing the resource allocations and also operational efficiency. And the objective of this talk is to present a district heating demand forecasting with a 24-hour prediction horizon. This model is adaptable to different scales depending on data availability. So the idea is to present 3 different modeling format. The first one is using a traditional machine learning model. We are using district heating data set. The data set is along 3 years time period with a hourly resolution. So the district heating hour by hour. We have the information about the energy consumption per building. We have around 2,460 buildings composing our data set. And we also have the water volume, the water temperature, the inlet and outlet temperature for each building. Also, we have building characteristics. I mean, the building type, if it's residential or an office, the total area and the number of rooms. And we take into account also some weather information like the external temperature. As said before, the output of our models is 24 horizon district heating energy consumption. Well, we have applied 3 different modeling techniques. First one is random forest, XGBoost, and feed-forward neural network. We are comparing them. Here we have a sample of the buildings to show you the difference between each model and each machine learning technique. We can see clearly that random forest has the worst performance, and XGBoost and feed-forward neural network has similar performance, but at the end, feed-forward neural network is outperforming the rest of the techniques. So at this point, we chose the feed-forward neural network as a baseline for the rest of our experiments. Traditional machine learning techniques, as you should know, data are used and are stored in the same place, and the models are trained where the data are. I mean, if you have a server, you store your data in this server and train your model by uploading your data and train your model. This is the traditional machine learning techniques. We have other paradigms like the federated learning. It's slightly different, and this technique is privacy by design technique, in a way that data doesn't leave the source of the data. In the case of district heating, data are registered on the smart meters, and the smart meters are located in each building. So the idea here is to train models on devices locally, and this brings privacy to the model that we are using to train a global model to make the district heating forecasting. So the idea here is first train the model locally, send the weights of the model to the central model, and then in the central model we aggregate the weights and send back the aggregated model to all the nodes. This offer, in addition to the privacy, offer more scalability. Since if you need to add more meter IDs, so you don't have to retrain all your model. You only share the aggregated model to the new nodes and start to train your models locally and send the updates to the central node. Okay, the federated learning brings privacy, scalability, but there are some challenges with the federated learning paradigm. One of them is the data heterogeneity. In case of district heating, there are a lot of patterns, difference in energy consumption between a building and another. So to capture this heterogeneity, we present the multi-center federated learning. The idea here is not having a unique and single central model. Instead, we have different central nodes, and this is performed by clustering the weights gathered from the different nodes. So it depends, the number of the central models depends on the clustering result, and the nodes or the binding will receive the aggregation of their corresponding cluster central node. So here we have a comparison between the monolithic, the baseline model, which is modeled with the feed-forward neural network, the federated learning, and the multi-center federated learning. We clearly see that the traditional machine learning techniques outperform the federated learning techniques, so they are more accurate. But in the other part, the federated learning paradigm brings scalability and privacy. Here we have the federated learning is the worst performing in terms of accuracy, but the multi-center federated learning comes as a balance between the monolithic models and federated learning models. So we have on one side the privacy, the scalability, but also the accuracy of the machine learning models to make the 24-hour district heating energy consumption forecast. So as a conclusion, the monolithic model achieves the highest accuracy, but the federated learning ensures privacy. It's GDPR compliant, and also it's more scalable than the other machine learning methods. The multi-center federated learning addresses data heterogeneity, delivering higher accuracy than standard federated learning models. And an important point here is that this framework that we have developed under the framework of PRELUDE project can be generalized and applied to any other energy forecasting task. So it may be applied to electricity or water consumption, etc., etc. And that's all. Thank you very much for your attention.
Not the right button. Okay, so I'm Bernard Paule from ESTIA. We are a company located in Switzerland, in Lausanne, on the campus of Swiss Federal Office for Technology, EPFL. I represent one of the tasks of this PRELUDE project. The task is, the name is Building Renovation Roadmap. The idea was to work on an application that could allow the key partners in a building renovation to make decision with prioritization of the actions, and also a link to the costs linked to these actions. So this work was done with CORE, presented by Valia just before. So we at ESTIA worked on the renovation rules, and CORE worked on the development of the application. So the idea is that when you face a building, an existing building, there's a lot of topics to handle, and it's complex. There are overlapping issues because sometimes you will optimize one field, for example, heating, and you will depress another one, like lighting or cooling or whatever. So the idea is to have a global overview and to determine priorities and costs, as I mentioned before. Another point that is important is that many information are either not complete or not accurate because it's existing buildings with no precision, no IA data or whatever regarding the composition of the building and whatever. And there are also multiple players that are acting in a renovation process. You have architects, you have engineers, you have financial people and or whatever. And the idea is to be able to give incentives, having a broad vision of the problem, giving the priority, and also we decided to use plain language in order to be understandable by all these players. So the main idea is to get the information that you have at the end of an energy performance certificate, EPC, and gather this information and to treat it to make this prioritization and give the incentives. So we choose to handle fuzzy logic rules to do that because fuzzy logic is able to manipulate imprecise values and also to handle linguistic items and so to deliver a message that are quite intuitive. So the idea is for each topic, for example, heating, energy consumption, to select a key parameter. For heating, the key parameter is the energy consumption because it's normally known. So you look at this parameter and we decide if it's very low, moderate, to very high. And if this key parameter is moderate, high, or very high, then we have to look at the parameters that could be improved. So the idea is that with fuzzy logic, we are able to handle different positions. So the energy consumption could be at the same time quite high and quite very high. And it's not just a Boolean technique and with different solutions at the end. For example, if you look at energy consumption, it's high on this example with a truth level of 0.64 and at the same time very high with a truth level of 0.36. It's a detail, but if we have this and if on another hand we have the information regarding insulation thickness from 0 to 20 or to 30 centimeters for the walls, for the facade, for example, we are able also to say that it is in the same time slightly unfavorable and favorable and unfavorable. And the idea is to translate all this combination between the key parameter and the detailed parameters and to make decision tables. So if the key parameters is on the status and the associated, then we would like to deliver slight, strong, or imperative incentive regarding the key parameter. And transferring that into into language, intuitive language, it means that a strong incentive will be you should modify this parameter. If it's very strong, it's you must, or if it's slight, you could. So here, when compiling all the presentation, the message for the should is hidden by the logos, but it could be you can imagine what we want. You should improve, I don't know, the insulation thickness of the walls, or change the boiler, or whatever. Yes, yes. So regarding the application, so you have an application that first deals with the description of the building, the function, the location, the dimensions, composition of the different walls and the windows and shading. Then you have a topic dealing with heating. So the key parameter, as I mentioned, is heating energy consumption, the effective, measured. And based on the Swiss requirement, we took the Swiss requirements regarding the targets of energy consumption, and we made a climatic adaptation to be able to handle a building either in Norway or in Greece. And the associated factors are the one we can modify, or the tenant, or not the tenant, the owner or whatever, could make modifications. So facades, windows, composition, technical parameters, technical systems, and so on. For the cooling topic, I'm sorry, not at the right place, but not important. The key parameter is the intrinsic overheating risk. And by that, we mean all the parameters that we cannot modify. So the location, the environment of the building, is it urban or in the landscape, the function of the building, the glazed area, and the thermal mass of the building. We will not change that when renovating a building. So this is an intrinsic overheating risk. And then the associated factors are the shading device, the openable area for natural ventilation, the technical settings if there is a cooling system, and so on. For the lighting, it's another approach. The key parameter is obsolescence. So we will not have all the list of the lamps in an existing building, but we will just look at the main types of lamps and luminaires, and also how it's controlled, switched on and on and off. Sorry, if there regulation or dimming or whatever, or zone lighting. So, and we adapt the incentives according to the room function or the building function. We will not give the same incentive for housing or for office building or open office building, and so on. And then regarding renewable energy sources, which is the last topic of the application, we base on the RES selector, renewable energy selector developed by Core as a standalone tool in another part of this PRELUDE project. Not been mentioned, but it has been done. And at the end of the description of the building and the different parameters, then the application is able to give for each topic, heating, cooling, and so on, a list of actions with prioritization based on language items. You must, you should, and you could. And here you have the actions in very simple sentences. And the last thing of this application, and not the less important, is we made a link with Epicure database. Epicure is also an application issued from a European project. And in the beginning of the PRELUDE project, we translate the original Epicure from a software a desktop version to an application, a web app application. So now we are able to take some costs from this database. Not all the incentives could be associated with the cost, because in the Epicure database, there is also a link with the degradation status of the element. And here in the roadmap, we don't have any information regarding degradation status. But the idea is to pick up some costs and then not to make an addition, because some costs are missing, but to make to give another idea of the owner or whatever, to make a decision. The idea is to make decision. Just a few words about this Epicure database. We have in Switzerland more than 30 years of experience using these methods. So thousands of buildings have been handled with that. So the cost database is quite strong. We used to say that we have a 15% precision regarding the overall cost when we make an analysis. The costs are related to the dimensional coefficient of the building. So, and also there is an adaptation to the cost index, European cost index, to adapt for other countries, because we are an European project. So I think it's okay. It's all.